Greetings, fellow travelers of the cosmos. Today, we embark on a thrilling expedition to the forefront of robotics, where the lines between biology and technology blur. Imagine robots that move and adapt with the grace and efficiency of living organisms. This is the promise of Biohybrid Robotics, a revolutionary field fueled by the creation of synthetic muscle networks. Traditional robots, while impressive, often pale in comparison to the elegance and adaptability of their biological counterparts. Their rigid metallic limbs and gears lack the fluidity and efficiency of muscles, the very essence of animal movement. But what if we could bridge this gap, harnessing the power of living tissues to create robots that are more lifelike than ever before? This is where Biohybrid Robotics steps in, merging the intricate designs of nature with the precision of engineering. By integrating living muscle tissues with artificial components, scientists are creating a new breed of robots that can potentially revolutionize various fields, from medicine to exploration. Imagine robots that can navigate complex terrains with the agility of a cheetah, or assist surgeons with the dexterity of human hands. These remarkable feats are made possible by synthetic muscle networks, the powerhouse of biohybrid robots. Meticulously engineered from living cells, they mimic animal movement. Picture these networks as miniature versions of our muscles, a testament to human ingenuity. Scientists culture cells on biocompatible scaffolds. These scaffolds guide cells to form functional tissues. Stimulated electrically or through light, they generate movement. Like a conductor, stimuli trigger synchronized contractions. Imagine robots with the gentle touch of a human hand, or moving through water like an eel. This technology promises to reshape industries. In the next section, we delve deeper into advancements, from soft robots navigating delicate environments to biohybrid limbs restoring mobility to amputees. For decades, robotics has been dominated by machines crafted from metal and wires, their movements dictated by motors and gears. These robots are indispensable in industries, from manufacturing to exploration. Picture assembly lines where robotic arms work tirelessly. Powered by electric motors or hydraulic systems, they excel in strength and precision. Think of robotic welders in car factories, fusing metal parts with accuracy, or robotic explorers traversing harsh terrains of other planets. However, they often fall short in replicating the fluidity and adaptability of biological systems. Their movements can feel rigid and mechanical. Imagine a robot navigating a cluttered room, struggling to adapt. This stems from their actuators, responsible for movement. Electric motors can be bulky and lack fine control. Hydraulic systems rely on fluids and pumps, prone to leaks. These limitations are evident when interacting with delicate objects or navigating complex environments. Traditional actuators struggle with delicate tasks in unpredictable environments. In surgery, rigid grasps can damage tissues. In search and rescue, they face unpredictable hazards. Their rigidity limits adaptability and effectiveness. Traditional actuators lack energy efficiency. Muscles convert energy efficiently. Motors and hydraulics lose energy to friction and heat. This affects mobile robots significantly. They need bulky batteries and frequent recharging. This limits their operational range and autonomy. Section 3. Biohybrid Actuators, a paradigm shift. Biohybrid actuators offer a paradigm shift in robotic actuation. They integrate living muscle tissues, harnessing nature's capabilities. Imagine a robot powered by actual muscle fibers, replicating animal movement. This opens up a realm of possibilities, enabling robots to interact with greater dexterity and efficiency. Picture a robot with a biohybrid hand as precise as a human hand, bridging the gap between the artificial and the natural. Imagine biohybrid robots assisting in surgery or exploring rainforests. Biohybrid actuators promise to revolutionize our interaction with machines. Next, we delve into synthetic muscle networks. Section 1. Engineering life, the making of synthetic muscle networks. Imagine stepping into a lab where scientists craft living tissues, the building blocks for a new era of robotics. This is the world of synthetic muscle networks, the heart of biohybrid actuators. These networks mimic the intricate structure and function of our own muscles. It all starts with a muscle cell, nurtured in a controlled environment. These cells, known as myocytes, contract and relax, generating movement. Think of them as microscopic engines, awaiting the right signals. They need a framework to guide their growth and organization. Biocompatible scaffolds act as blueprints for muscle networks. These scaffolds provide support and biochemical cues for cell alignment and differentiation. The choice of scaffold material influences the muscle network's properties and functionality. Scientists select materials that mimic the natural environment of muscle tissues. Section 2. Scaffolding success. Guiding cellular architecture. Imagine these scaffolds as intricate lattices, guiding the growth and alignment of muscle cells. The scaffold's architecture shapes the muscle network's form and function. Think of it as weaving a tapestry, each thread creating a pattern. Scientists tailor scaffolds for specific applications. Aligned fibers mimic skeletal muscle for rapid contractions. Interwoven structures resemble cardiac muscle for rhythmic contractions. Scaffolds provide structural support and nutrient flow. Porosity allows diffusion of nutrients and waste removal. Think of it as a miniature circulatory system. Scaffolds can be functionalized with bioactive molecules. These molecules guide cells to form functional tissues. The creation of the muscle network is only half the story. To harness their potential, these networks need activation. Electrical stimulation mimics our nervous system. It triggers synchronized contractions, generating movement. But it has limitations like muscle fatigue. Scientists explore optogenetics, using light to control cells. Light precisely controls muscle contractions. Creating a functional muscle network in a petri dish is a remarkable feat, but the true test lies in integrating these living actuators into robotic systems, transforming them from biological curiosities into powerful tools for real-world applications. Imagine these muscle networks as engines carefully crafted and tuned, awaiting installation into the robotic chassis that will become their vehicles for interaction with the world. This integration process requires a delicate touch, seamlessly merging the biological and the artificial. Scientists must carefully consider factors like biocompatibility, ensuring that the materials used in the robotic components do not harm the living muscle tissue. They must also design interfaces that allow for efficient force transmission between the muscle network and the robotic components it is meant to control. One approach involves encapsulating the muscle network within a flexible, biocompatible membrane, creating a self-contained actuator that can be easily integrated into robotic limbs or grippers. This membrane acts as a protective barrier, shielding the muscle tissue from the external environment while allowing for nutrient diffusion and waste removal. Another approach involves directly attaching the muscle network to the robotic components, using specialized adhesives or anchoring points. This method allows for more direct force transmission, potentially increasing the actuator's power and efficiency. Imagine a world where robots move with the fluidity of living organisms, seamlessly integrating into our lives. This is the promise of biohybrid robotics, transitioning from science fiction to reality. Recent strides showcase synthetic muscle networks and functional devices. Collaborative efforts are paving the way for a new generation of robots. Soft robotics inspired by nature is making significant inroads. Imagine robots navigating confined spaces with the agility of an octopus. Their soft bodies conforming to surroundings, manipulating delicate objects. These robots navigate complex environments with ease, ideal for exploration, search and rescue, and minimally invasive surgery. Section 2. Soft robotics, where biology inspires flexibility. Soft robotics shine by mimicking biological systems. Traditional robots struggle in natural environments. Their rigid limbs and wheels get stuck. Biohybrid robots use flexible materials to mimic nature. They adapt to environments and squeeze through spaces. Their inherent safety is a key advantage. Unlike traditional robots, soft robots are compliant. They absorb impacts, minimizing injury risks. Ideal for healthcare and personal assistance. Imagine them aiding in therapy or providing companionship. Section 3. Biohybrid limbs, restoring mobility, empowering lives. The dream of restoring lost limbs has long captivated the human imagination. Traditional prosthetics often fall short of replicating natural movements and sensory feedback. Biohybrid limbs powered by synthetic muscles offer hope, promising to bridge the gap between man and machine. Imagine a future where prosthetic limbs move and feel just like real ones. Section 4. Air-operated muscles, breathing life into robotics. Researchers are exploring air pressure to power biohybrid robots, mimicking biological muscle movements. Air-operated muscles, made from silicone or rubber, expand and contract with compressed air. They are lightweight, compliant, and safe, ideal for human interaction. Applications include prosthetics, exosuits, and wearable devices. Imagine a gardener tending to a delicate orchid, carefully regulating its environment to ensure its survival. Similarly, scientists working with synthetic muscle networks face the constant challenge of maintaining the viability and functionality of these living tissues outside their natural environment. These microscopic powerhouses, while capable of remarkable feats, are also incredibly sensitive to their surroundings. Like prima donnas of the cellular world, they demand a precise cocktail of nutrients, oxygen, and growth factors to thrive. Imagine trying to keep a delicate flame alive, constantly shielding it from drafts and ensuring a steady supply of fuel. One of the primary hurdles lies in replicating the intricate network of blood vessels that nourish muscles within the body. Without a constant supply of oxygen and nutrients, these energy-hungry cells quickly succumb to fatigue and eventually perish. It's like trying to power a car engine without a fuel pump. Eventually, it's going to sputter and die. To address this challenge, researchers are exploring various strategies, such as incorporating microfluidic channels within the scaffolds to mimic blood vessels, delivering nutrients directly to the cells. Others are experimenting with oxygen-carrying molecules or biocompatible materials that enhance oxygen diffusion, ensuring these tiny powerhouses can breathe. Imagine trying to play a complex symphony on a piano using only one finger. You might be able to hit the right notes, but the performance would lack nuance and control. Similarly, achieving precise and coordinated contractions in synthetic muscle networks remains a significant challenge, akin to mastering a delicate dance between electrical signals, mechanical forces, and biological responses. While electrical stimulation offers a relatively straightforward method for triggering contractions, it often lacks the finesse required for fine motor control. It's like using a sledgehammer to crack a walnut, effective, but not exactly subtle. Imagine a biohybrid hand trying to pick up an egg with such a blunt instrument. The results would be disastrous. To overcome this limitation, researchers are exploring more sophisticated control strategies. Optogenetics, for instance, offers a promising avenue, allowing for targeted stimulation of specific muscle fibers using light. It's like having a conductor's baton, precisely cueing in different sections of the orchestra to create a harmonious symphony of movement. Other approaches involve developing biocompatible electrodes that integrate more seamlessly with the muscle tissue, minimizing damage and improving signal transmission. Imagine these electrodes as tiny whispers, gently coaxing the muscle fibers into action rather than shouting commands. Imagine a marathon runner hitting the dreaded wall, their muscles screaming for respite after pushing their limits. Similarly, synthetic muscle networks, while initially bursting with energy, face the inevitable decline in performance over time. Their lifespan, often limited to days or weeks, poses a significant hurdle for their integration into long-term applications. This decline stems from a multitude of factors, including the buildup of metabolic waste products, the degradation of the scaffold material, and the inherent limitations of cell division. It's like a car engine slowly wearing down over time, its performance gradually diminishing with each passing mile. To address this challenge, researchers are exploring strategies to enhance the longevity and durability of synthetic muscle networks. One approach involves optimizing the culture conditions to minimize cellular stress and promote cell survival. It's like providing the perfect nurturing environment for a delicate plant, ensuring it thrives for as long as possible. Other efforts focus on developing biocompatible materials that resist degradation and support long-term cell viability. Imagine these materials as resilient scaffolding, providing a sturdy framework for the muscle cells to cling to and function optimally. Imagine a world where robots, no longer cold, metallic entities, but beings infused with the essence of life, walk among us, their movements mirroring the grace and fluidity of nature. This is not a scene from a science fiction movie. This is the future that biohybrid robotics, armed with the power of synthetic muscle networks, is poised to create. The potential applications of this technology are as vast as our imagination. Imagine biohybrid robots working alongside humans in factories, their movements so precise and delicate that they can assemble intricate devices with the dexterity of a master craftsman. Picture these robots deployed in disaster zones, their flexible bodies navigating rubble and debris, searching for survivors with unwavering determination. The integration of biohybrid robots into our lives holds the promise of not just augmenting our capabilities, but also fundamentally changing the way we interact with machines. These robots, with their lifelike movements and adaptability, have the potential to break down the barriers that have traditionally separated humans from their artificial creations. In the following sections, we'll delve into specific domains where biohybrid robots are poised to make a transformative impact, from revolutionizing healthcare to pushing the boundaries of exploration beyond Earth. Section 2. Medical Marvels, Biohybrid Robots in Healthcare. Step into the operating room of the future, where the surgeon's scalpel is guided not by human hands alone, but by the precise movements of a biohybrid surgical robot. Imagine a world where surgeries are performed with unparalleled precision, minimizing invasiveness and reducing recovery times. This is just one facet of the transformative potential of biohybrid robots in healthcare. Imagine biohybrid robots assisting surgeons in delicate procedures, their movements controlled by the subtle contractions of synthetic muscles, mimicking the dexterity and precision of the human hand. These robots could navigate the intricate pathways of the human body with minimal disruption, delivering targeted therapies, or performing complex reconstructions with unmatched accuracy. Beyond surgery, biohybrid robots hold immense promise for rehabilitation and assistive technologies. Imagine exoskeletons powered by synthetic muscles, helping stroke victims regain mobility or assisting individuals with spinal cord injuries to walk again. Picture biohybrid prosthetic limbs that move and feel like real limbs, responding to the user's intentions with intuitive grace. The integration of biohybrid robots into healthcare has the potential to alleviate human suffering, enhance quality of life, and redefine the boundaries of what's possible in medicine. Section 3. Beyond Earth Biohybrid Robots as Explorers. As humanity sets its sights on the stars, biohybrid robots emerge as ideal candidates for pushing the boundaries of exploration beyond Earth. Imagine robots that can withstand the harsh conditions of other planets, their resilient bodies adapting to extreme temperatures, radiation, and unforgiving terrains. Imagine biohybrid robots exploring the icy plains of Europa, their movements mimicking those of aquatic creatures searching for signs of life beneath the frozen surface. Picture these robots traversing the dusty landscapes of Mars, their flexible limbs navigating treacherous canyons and scaling towering mountains, collecting valuable data and searching for resources. Unlike traditional robots, which are often limited by their rigid structures and reliance on complex control systems, biohybrid robots offer a unique combination of resilience, adaptability, and autonomy. Their ability to learn and adapt to their surroundings makes them ideal for exploring the unknown, where unexpected challenges and opportunities abound. The use of biohybrid robots in space exploration not only extends our reach into the cosmos, but also allows us to study other worlds with minimal disturbance, preserving their pristine environments for future generations. Section 1. The Dawn of a New Era in Robotics. As we stand on the precipice of this biohybrid revolution, it's hard not to feel a sense of awe and anticipation. The integration of synthetic muscle networks into robotic systems marks a paradigm shift, a departure from the rigid mechanical constructs of the past. Imagine a world where robots become integral parts of our lives, seamlessly assisting us in ways we're only beginning to imagine. This new era of robotics is about creating robots that can coexist and collaborate with humans in ways never before thought possible. Section 2. Embracing the Biohybrid Future. The road ahead for biohybrid robotics is paved with exciting opportunities and challenges. Researchers refine techniques for culturing and controlling synthetic muscle networks. The quest for biocompatible materials and sophisticated control systems drives innovation. Biohybrid robotics raises important ethical and societal questions. How do we ensure responsible development and use? Addressing economic and social implications is crucial. These questions are essential as we navigate this new frontier. Biohybrid robotics is a journey of discovery and understanding life. Emulating nature unlocks new possibilities for lifelike, adaptable machines. The future of robotics is biohybrid, brimming with boundless possibilities.